Alright, so welcome back to AC. So now that we have a bit of an understanding of how AC works, we're going to start to look at how different components behave in an AC circuit. More specifically, we're going to be looking at resistors, capacitors, and our inductors, okay? And in this video, we'll be specifically talking about how capacitors behave in an AC circuit, okay? So if we look at what happens to capacitors in DC, okay, as a quick reminder, so we have a circuit here and there's a light bulb, okay, and it's connected like so, okay? If we were to turn on this circuit, and so now our power supply is supplying a current into the circuit, this lamp is going to glow, okay? Briefly, however, only briefly. So it's going to glow initially. However, due to this capacitor, as we know, charge is going to build up on this capacitor plate. Okay, and therefore this charge is going to repel any oncoming charge, and so therefore the current is going to die down. And then when the current dies down, the lamp is going to go dim once more, okay, and no longer shine. So therefore our lamp will glow for a brief period of time, and this is due to the fact that current eventually stops in a DC circuit, okay, with a capacitor, that is, okay. In contrast, for alternating current, okay, so this is what our alternating current source will look like. We have a little sinusoid or sine graph within our source, okay? In contrast, when we have a alternating current and a capacitor with the exact same setup where we have our light bulb over here, okay? In this scenario, our current is constantly changing directions. And because of that, let's say this is a 240 volt RMS source with a 50 hertz frequency, okay? And so therefore this means that the current is swapping directions 50 times within a second. And so because of the fact that the current is constantly swapping directions, in this case, our lamp will continuously glow, okay? And it will glow forever so long as the power supply can supply a current. And the reason for this is because initially, the power supply will put charge onto this side of the plate, but before charge can build up, the current direction is reversed into this direction now, and then charge will slowly to build up over here. But before a sufficient amount of charge can build up on the capacitor plates such that it will repel the oncoming current, the current changes directions again, okay? And so that continuously happens, and so the capacitor cannot build up enough charge to start to repel the oncoming current, okay? And so that is why there's always going to be a continuous flow of current through that light bulb, and so the light bulb is going to continuously glow. Again, so long as the power supply can supply a current. Okay, so our lamp will continue to glow, alright? And so it's almost as if the capacitor isn't there, because before the capacitor can do what it usually does and it resists current, the current direction changes. So again, it's almost as if the capacitor isn't there. However, in reality, the capacitor is there, and the capacitor is slowing down the current, even if it's just by a little amount, okay? And so we can say that in an AC circuit, capacitors do impede the flow of current, okay? And this is to a degree, okay? And the reason why I say to a degree is because, as I discussed over here, the capacitor in AC does not stop the flow of current completely like it does in DC, okay? So it only impedes the flow of current by a small amount, and so that's why I've mentioned that it only stops the current to a degree, okay? And so we can write that in, that it does not stop the flow of current completely, okay? And so before we figure out how much the capacitor impedes the current, I want to draw your attention to a quick reminder, and I want to remind you about the relationship between voltage and current in a component in a DC circuit, okay? So if we were to graph the voltage and the current right so, okay, and we were to have a circuit right here, okay, now let's say we have a resistor R over here, and this is a variable power supply, so we can change the voltage values. If we were to start with a small voltage value, we know that the current is going to be small like so. And as we increase our voltage values, we will get a straight line like so, okay? And we'll see a straight line trend like that, okay? And so assuming that this is a ohmic resistor, okay? And what I mean by an ohmic resistor is a resistor that follows Ohm's law, okay? So that's pretty much every resistor that you've looked at in NCEA, so that's all good. So assuming that this is an ohmic resistor, and therefore it follows Ohm's law, okay, so this relationship only holds true if this is an ohmic resistor. If this wasn't an ohmic resistor, then this line would not be straight, okay? So we have a straight line because we have assumed that this is an ohmic resistor, okay? And so what we can say through this straight line is that our voltage is directly proportional to our current, okay? So when our voltage increases, so does our current. So that means that the voltage across an ohmic resistor is directly proportional to the current that flows through that ohmic resistor, okay? And so this is saying that the voltage is directly proportional to the current. However, we can make an equation out of this, and we can say that the voltage is equal to some constant, which we can call K, multiplied by the current, okay? And in this case, this constant is going to be the gradient of the line, okay? And we know that this gradient is our resistive value, okay? And so we can replace this with an R. And as you can see, we get Ohm's law right there, okay? So a very, very similar thing happens when we look at a capacitor in an alternating current circuit, okay? So if we put an AC power supply, okay, and we hook that up to a capacitor, like so, and we were to graph the voltage and current, as we increase the voltage, we'll again see the same straight line trend, where as we increase the voltage, our current also increases, okay? And so we get our straight line like so. And so once again, we can say that the voltage is directly proportional to the current. And therefore the voltage is equal to some constant K multiplied by the current. And so what is our constant in this case? Once again, it is the gradient of this graph, okay? And what we call this is X of C, okay? Where X is our reactance and C obviously means capacitor. And so X of C stands for the reactance of the capacitor. And so therefore we can replace our constant K with our X of C, or our reactance of our capacitor. And more commonly you'll see this be written as V is equal to I X of C, like so. So what is reactance, okay? As you can see, it's pretty similar to resistance in DC circuits. And you'll be right, it is pretty similar to resistance. Our reactance is the property of a component that limits the current from an AC supply, okay? So as you can see, this is pretty similar to resistance, because resistance is the property of the component that limits a current from a DC power supply. However, reactance is the property of a component that limits current from an AC power supply, okay? And it's important to note that this is also given in ohms, okay? So the unit for reactance is also ohms, so same as resistance. So there are two factors that influence the reactance of a capacitor, okay? The first one being the frequency of the AC power supply, okay? So let's look into this. Let's see, we have our AC power supply right here, and we have our capacitor, like so, okay? As stated previously, at a high frequency, our current swaps direction very, very quickly. So it swaps from back and forth very, very quickly, okay? And so this prevents large amounts of current from building up, okay? So it prevents this process of large amounts of currents building up on the plates. And because we know it is the large amount of current that builds up on the capacitor plates which causes the capacitor to resist oncoming current. If the frequency of an AC power supply is high and therefore the charge cannot build up on the capacitor plates, therefore the capacitor is going to resist current less. Okay? And so the property that we're interested in this case is our angular frequency, and remember that's equal to 2 pi f, okay? And so therefore, if we increase our angular frequency, therefore the reactance of the capacitor will decrease. And so therefore we can say that the angular frequency and the reactance of our capacitor are inversely proportional to each other, okay? The second property is the capacitance of the capacitor. So if the capacitor has a higher capacitance, that means more charge can be stored on the plates of the capacitor. And so if we think about what causes the capacitor to resist oncoming charge, it's the fact that when the capacitor is quote-unquote full, and therefore no more charge can be placed onto the plates of the capacitor, that's when it starts to resist charge, because there's no more room for more charge to accumulate. And so if the capacitor has more room for charge to accumulate, aka it has a larger capacitance, therefore the capacitor is less likely to resist oncoming charge, okay? And so once again, if the capacitance of our capacitor is increased, therefore the reactance of our capacitor will decrease. And so we can say that the reactance of our capacitor is inversely proportional to the capacitance of the capacitor. And so therefore, from this, we can form an equation, and we can say that the reactance of our capacitor is equal to 1 all over the angular frequency multiplied by the capacitance, okay? And so this is our equation, where this right here is the reactance of the capacitor, which we know is measured in ohms. This is the angular frequency, which we know is also 2 pi f, okay? Or we can say that's 2 pi all over t, okay? And we know that's measured in radians per second, okay? And this is our capacitance, and we know that's measured in farads, okay? And so now that we have all this knowledge, I think it's time to do a practice question. Let's say we have an AC power supply, and this is a 12 volt RMS power supply with a 50 hertz frequency. Okay, and this is connected up to a capacitor which has 100 microfarads of capacitance, and we hook it up like so. And what I want to do is determine the current, or our I value, right? Remember that this I value is actually our RMS value, okay? And so you can pause the video and give that a try. So the first thing that I would do is first find out our reactance of our capacitor. We know that's equal to 1 all over the angular frequency times the capacitance. We know our angular frequency is equal to 2 pi f. We are given our frequency, and so therefore our angular frequency is equal to 2 pi times 50, and so therefore our angular frequency is 100 pi, okay? And so therefore we can plug in our numbers, 1 all over 100 pi multiplied by 100 times 10 to the negative 6, because this is microfarads, okay? And this gives a reactance of 31.83 ohms, okay? And so therefore we know our VRMS is equal to IRMS multiplied by our reactance. We are trying to find our IRMS. We are given our VRMS, and we just found our reactance. And so therefore we can rearrange for our I value. We get IRMS is equal to VRMS all over our reactance. And this gives 12 all over 31.83. And that's equal to 0.38 amps. There we go. Now remember, this is our RMS current, and therefore this is not the absolute current value. Remember, this value is going to fluctuate because our RMS is a type of average, okay? So just a quick reminder right there. But other than that, that'll be it for this video. See ya.